Hello everyone, welcome to the 8th experiment of the General Chemistry Science Lab. So what we are going to do in this experiment, we will introduce you the chemical equilibrium and the Le-Chatelier principle. So what we're going to do here is a chemical equilibrium, as you guys know, is a state or it's a condition at which two reactions, like a forward and backward reaction, they take place at the same rate or at the same speed. Okay, so what we're going to do here is we introduce you a bunch of chemical equilibrium reactions, and we see each reaction and we change the conditions of the reaction. Then we see how the equilibrium responds to the change in condition. So when we say change in condition, what we mean here is we can change either the temperature or we can change either the concentration of reactants or products. So as a part one of this experiment, we're gonna make a chemical reaction between an aqueous solution of copper with ammonia. Okay. On the same time, we have one more experiment. In that, we're gonna make a chemical reaction that is an aqueous solution of nickel with ammonia. So first we see the reaction of copper, aqueous solution of copper with ammonia. So what we're going to do here is, as I told you, we take an aqueous solution of copper and we react that aqueous solution with ammonia. So once the reaction takes place, we reach this equilibrium. So you can see here in the left hand side, we have the aqueous solution of copper and other reagent is ammonia. When you react them, we will get the product, that is copper amine complex and water also. So you look at that here. The aqueous solution of copper, which is in blue color, so once the reaction proceeds, once you get the product, you look at the product here, the color of the product is dark blue. So once you do this reaction, we can watch the color change in the test tube. So what will happen here is the slight blue solution slowly turns to dark blue. That means we reach the equilibrium. So first we're going to see this equilibrium in the test tube right now. Okay, so we're going to do the first reaction, that is the aqueous solution of copper reacts with ammonia. So what we need for this test, it's very simple. We need a copper sulfate solution. So this is the copper sulfate solution. That means copper sulfate dissolved in water. So that's aqueous solution. Okay, then we need ammonium hydroxide, the concentrated ammonium hydroxide. We also need 1 molar hydrochloric acid. So how does this reaction works? So you'll go to the test tube, take a clean and nice test tube. So we're going to add probably around 10 drops of your copper solution. So as you know that the copper solution is having light blue color. So I'm going to add probably around 1 ml of the solution is more than enough. So this is a copper sulfate solution. As you can see, this is a copper sulfate solution, means aqueous solution of copper. So you can see in the equation, it is having a slight blue color. It is actually copper tetrahydroxy complex. So it's having a slight blue color. So now what I'm going to do, I'm going to add ammonia into this test tube. So we'll go to ammonium hydroxide. So again, I'm going to take probably around 10 drops of ammonium hydroxide and slowly add ammonium hydroxide into this test tube. So once you add, should be fine, around 5 drops. I just added 5 drops. By that I got a deep blue color. So this is the product actually. This is the copper amine complex. Now if you shake it for some time, if you keep it aside the test tube, so the equilibrium is already established. Okay, now you got the equilibrium. You have the solution here, which is having a dark blue color. Now we are going to disturb this equilibrium. Okay, so how do you disturb the equilibrium? We can change the concentration of either the reactants or the products. So just to disturb the equilibrium for this particular reaction, we have HCl here, the concentrated HCl. Sorry, it's the 1 molar HCl. So take the 1 molar HCl, then you open the test tube and add probably around 10 drops into the test tube. So I'm going to take the test tube out, then you can see what's happening. So you can see that the solution is slowly getting light, and the color, the dark blue color, is slowly getting faded. Because as I added a lot of ammonium hydroxide in the first part, I need to add a lot of HCl, because this HCl is not really that much concentrated. That's why I need more HCl to make a significant change in the equilibrium. So you can see that now the color is getting faded. So we almost reached a point at which you can see there is a remarkable change in the color. Now the solution is slightly turned to pale blue. So now there is a change in the direction of the equilibrium right now. So I can explain that by the help of the equation. So as we have seen, this is the equilibrium reaction, what we dealt right now. So what I did now here is, after establishing this equilibrium, I added HCl into the test tube. So you know that as this is equilibrium, you know both forward and backward reaction takes place at the same rate. So in your test tube, you have both reactants and the products. So when I added the concentrated HCl, or 1 molar HCl into the test tube, the HCl being an acid that reacts with the ammonia base. So once the HCl reacts with the ammonia base, what is happening? The concentration of the ammonia in the equilibrium is decreasing. So once the concentration decreases, see, ammonia is in the left side. So according to the Le Chatelet principle, the equilibrium will shift from right to the left. That's why we can see the color change. So the equilibrium is eventually it is changing from the dark blue. The color is changing from dark blue to the light blue. So by looking at the color change, we can predict the direction of equilibrium, how the equilibrium changes in response to the change in concentration of the reactants. So in this experiment, we changed the concentration of ammonia just by adding HCl. Okay, so now we are going to do another equilibrium between an aqueous solution of nickel and ammonia. So the reaction is, you can see in the blackboard. So the reaction is just like this. So we have the nickel hexaqua. This is the aqueous solution of nickel. We react the solution with ammonia. So once the reaction takes place, so you will get the nickel amine complex in the solution. So as you can see here, this is having a slight green color of the solution, and once you get the product, this product here on the right side, this is having a pale violet color. So you can still, again, as we have discussed in the last session, you can see the direction of equilibrium, in which direction the equilibrium moves, just by watching the color change. So to do this reaction, again, we need aqueous solution of nickel, so we can use nickel chloride. This is a nickel chloride in water. So nickel chloride in water, it's going to give you nickel hexaqua complex, what you have seen in the previous equation. So this is having a green color, and we need concentrated ammonia here. This we have ammonium hydroxide, and also we need concentrated HCl from the next part of this, the same reaction. So we will do the reaction right now. So I'm going to take the nickel chloride solution. So I will add probably around 1 ml of the solution into the test tube. So you can see it's having a pale green color. So now I'm going to add the base, the ammonia, into that. Take the ammonia. So how much ammonia you want to add? You just want to add drop by drop until you get a significant color change in the test tube. So you can hold the test tube in your hand and you add ammonia drop by drop. So as you add drops, you can see the solution slightly turns into light violet color. So I may need maybe a few more drops. Fine. So just want to shake it for a while. You can see the color is changed now. So this is the pale violet color. So this is the nickel amine complex. So now if you shake it for some time, the equilibrium can fastly achieved. So in a test tube now we have the equilibrium between nickel and ammonia. So I'm going to keep this equilibrium reactions here in the test tube. Now as the next stage, again I change the direction of the equilibrium. I disturb the equilibrium. So to disturb the equilibrium, again I'm going to use HCl, hydrochloric acid. Okay. So I'm home. Okay, this is the hydrochloric acid here. So take the hydrochloric acid and you have to add, hold the test tube, and you look at the test tube now, which is having a pale blue color of the solution. So I'm going to add HCl drop by drop into the test tube. So it seems like I need to add more volume of hydrochloric acid. Now it's slightly turns its color slowly. The color is changing, but it's really takes time. So I'm going to put this one here. I'll take a little bit more hydrochloric acid. The solution slightly turns into pale green, but you cannot really observe the pale green because I have too much volume of the solution here. That's why. So, but anyway, the pale violet color is totally getting disappeared. We add, slowly start to see the slight, very slight green color. So after you add HCl drop by drop, the solution turns to pale green again. So that means you are changing the equilibrium from right to left as per the equation. Okay, so as the next part of the experiment, we are going to make another equilibrium between cobalt ions and chloride ions. So what we're going to do here is we are taking aqueous solution of cobalt, then we react with chloride ions. So chloride ions we get from hydrochloric acid. Okay, so look at the reaction first now. So the aqueous solution of cobalt is here. This is cobalt hexa aqua complex. So this is the aqueous solution of cobalt, which is having a wine red color. And we react them with Cl- ion, chloride ions from the hydrochloric acid. So once the reaction takes place, we will get the product. The product is cobalt tetrachloro complex. With we get the side product as water, H2O. So you look at the product here, the cobalt tetrachloride, which is having a dark blue color. And your starting compound, cobalt hexaqua complex, is having a wine red color. So we actually track these two colors. So from that we can predict the direction of equilibrium once we disturb the equilibrium after adding another reagent from this reaction. Okay, to perform this reaction, we need cobalt chloride solution in water. So cobalt chloride solution in water will give you cobalt hexa-aqua complex, which is having a wine red color. And the next reagent is the concentrated hydrochloric acid. And another one we need is just the deionized water, distilled water. Okay, so go back to the test right now. So you take a clean test tube. So I'm going to add probably around 10 drops of this cobalt aqueous solution. It's a cobalt aqueous solution. If you can see that, it's having a very nice wine red color. So now I'm going to add Cl- hydrochloric acid into that. So I will use the concentrated HCl. Shake it for some time and see what's happening. You can see that now the color turns to a kind of dark blue. So it's supposed to be very dark blue color, but you remember that this is not really dark blue. It feels like a slight violet color. This is because of the equilibrium. Because as I explained, in the equilibrium we have both reactants and products. So we have the reactant, the wine red color reactant, and also we have the dark blue color product. That's why the solution looks like a little bit purple in color. So this is the equilibrium. Now you reach the equilibrium, so you can keep the test tube here. Now, as we have seen the previous experiment, we have to disturb the equilibrium. So how do you disturb the equilibrium? So you look at the to disturb the equilibrium for this reaction, we can use just the deionized water. So I'm taking the deionized water and going back to the test tube. So I'm going to add water into that. So you watch what's happening inside the test tube. After adding water, the solution turns back to its wine red color. So what does it mean? So we have to go back to the equation once again. So as you can see from this equation, so you look at the product side, we have water as a product. So what I did here is I took the test tube, and after this equilibrium, I added excess water into the equilibrium. So when I add excess water, so I'm actually increasing the concentration of water in the product side. So the system, according to Le Chatelier principle, system wants to adjust by itself so as to reduce the concentration and go back to the previous condition. So the only one way is that the water molecule has to react in the backward direction, and you will get more and more your cobalt hexa-aqua complex. So the direction of this equilibrium, the movement of this equilibrium, we can easily track just by observing the color change. Okay, so as a second part of the experiment, now we are going to establish equilibrium of sparingly soluble salts. So we have as a first step, we're going to do the equilibrium of silver carbonate. So silver carbonate is one of the sparingly soluble salt. So let's see the equilibrium reaction of silver carbonate. Okay, what we are going to do here is, in order to establish an equilibrium of silver carbonate, so this is the silver carbonate which is sparingly soluble. So if you take silver carbonate and throw in water, so only 99% of silver carbonate will remain as such, and 1% only will go into the solution. So you get an equilibrium like this between the ions and the undissociated silver carbonate. So how do you get this equilibrium? So what we're going to do here in this test, we take silver ions and then we take carbonate, then we mix them together, then we'll get the silver carbonate. So let's watch the reaction. Okay, we have here the silver nitrate solution. So silver nitrate is going to give you silver ions. And we have sodium carbonate here. The sodium carbonate is going to give you carbonate ions. So what we're going to do, we're going to mix the silver ions and carbonate ions together. Then that will give you the silver carbonate precipitate. So let's see the reaction. Take a test tube. Then we're going to take the silver ion solution. We're going to add probably 10 drops, 5 drops is fine. Then I'm going to the sodium carbonate, the base. Sodium carbonate. Add drop by drop. So you can see that when I added sodium carbonate, it forms a white precipitate of silver carbonate. So now we have the equilibrium between silver carbonate and the silver ions and carbonate ions in solution. Okay. Now, so once you have the equilibrium, then as we have done the last part, so we are going to disturb this equilibrium. So how do you disturb this equilibrium? So just to disturb this equilibrium, we are going to add nitric acid, 6 molar nitric acid into the equilibrium mixture. So I'm going to take the nitric acid and add drop by drop into the test tube. Just in one drop, when I add, the whole solution turns to be clear actually. So that means the precipitate dissolves. So the silver chloride dissolves. So how do you explain this reaction here? Once you go back to the equation, here we have carbonate as a reactant. So I add H plus ion from the nitric acid. So nitric acid, H plus ion from the nitric acid will react with your carbonate in the equilibrium mixture. Then it will give you H2CO3 carbonic acid. So what is happening here is I'm going to reduce, or I'm reducing the concentration of carbonate from the equilibrium mixture just by adding an acid. So once the concentration of carbonate is getting reduced, according to Le Chatelier principle, the equilibrium will shift left side. So that means when you look at the test tube, you can see more and more silver carbonate here, undissolved silver carbonate, it goes into the solution. That means by adding a 1 drop of acid, the precipitate seems to be dissolved in the reaction mixture. That means your reaction or the equilibrium is shifting from right to left. Okay, so now we are going to establish another equilibrium of silver chloride. So silver chloride is also a sparingly soluble salt. So how do you make this equilibrium? So you can go back to the equation on the board. As you can see here, the silver ions reacts with Cl minus ion and it will give you the silver chloride precipitate. Okay, so we're going to see this reaction right now in the test tube. To do this experiment, we need again the silver nitrate. The silver nitrate will give you the silver ions, and we have HCl here. This will give you Cl minus ions. So we go back to the test tube now. You take the clean test tube, take the silver nitrate, open and add maybe 1 or 2 or 3 drops. Less than 1 ml should be fine. You can see. Then you go to the HCl bottle. You open the HCl, then you add HCl, hydrochloric acid, drop by drop into the solution. Some time, you can see that once you add HCl, now we are getting the white silver chloride precipitate. Should be fine. So this is the silver chloride, so which is actually a sparingly soluble salt. So in your test tube, we have the equilibrium between silver ions, Cl- ion, and the solid silver chloride. So we're going to leave this one here. Now as the next job, we are going to disturb this equilibrium. So to disturb this equilibrium, I have here the ammonia. This is ammonia. So I'm going to open the ammonia bottle. And I'm going back to my equilibrium solution. And I'm going to add drop by drop into the equilibrium solution. So you can see that one drop, second drop, even this third drop itself, the solution turns colorless. So you can explain this observation also using the Le Chatelet principle. So as you go back to the equation over here on the blackboard, this equilibrium reaction, we have silver ions, chloride ions in the reactant side, and we have the silver chloride on the product side. So what we did now, we added ammonia into the equilibrium mixture. So ammonia, when you add ammonia into the equilibrium mixture, your silver ions from the mixture will react with ammonia, and you will get the silver amine complex, which is also a soluble product. Okay, so when you add ammonia into the reaction mixture, this reaction is taking place. Your ammonia is taking the silver ions from the reaction mixture. That means you are reducing the concentration of silver ions in this equilibrium mixture. So again, as per the Le Chatelet principle, the equilibrium will be shifted to left side so as to produce more and more silver ions in the solution. So you can see this equilibrium shift just by looking at the test tube, because your silver chloride, when it goes to the solution, when it turns to the reactant side, it dissolves. Silver chloride is sparingly soluble. It is insoluble in water, but once it goes back to silver ions, it dissolves in solution. That means the precipitate dissolves. That's what the observation we have seen. Right. Okay, now you go back to the test tube now. So we just added ammonia. So as you have seen, when you added ammonia, the white precipitate dissolves. Okay. Now what we're going to do, we are going to make another change. We're going to add another reagent, that is nitric acid. 6 molar nitric acid we have. So we're going to open the bottle. So you go back to the test tube. So we're going to add nitric acid drop by drop into the test tube again. So you see what's happening inside the test tube. As you can see, when I added the nitric acid, take some time, you can see the precipitate comes back. The precipitate comes back. The silver chloride precipitates again. So how do you explain this one, this observation? We may need to go back again to the board. Okay, so you remember that we added ammonia. Then when you added ammonia, I explained you the precipitate dissolves. So now you have a new equilibrium in the solution. Okay, so now we are going to add, or we added the nitric acid. The nitric acid gives you H+ ion. So when you add a nitric acid, the H+ ion is going to react with this new equilibrium. So your equilibrium reaction is having already NH3, ammonia, it's a base. So your H+ ion reacts with this base, and we're going to give you NH4+. So what is happening here? So when you add H+ ion, the concentration of ammonia in the second equilibrium is getting reduced. So again, as per the Le Chatelet principle, you look at the second equilibrium, it will shift to the left side. So once this equilibrium shifts to the left side, you will get more and more silver ions. So you already have Cl- ions in the test tube. So once the concentration of silver ion exceeds a particular limit, it will react with Cl- and the silver chloride will precipitate back. So we are going to do the last part of this experiment. So here what we are going to do, again, we are going to establish an equilibrium, and we see what is the effect of temperature on this equilibrium. So you remember that so far we have discussed about the effect of concentration of either the reactants or the product on the direction of equilibrium. But this one, we're going to see the temperature effect. So what we have to do here, so we have to take a cobalt solution. Again, we are taking cobalt chloride. We have cobalt chloride here, aqueous solution of cobalt chloride. Okay, so aqueous solution of cobalt chloride gives you cobalt hexa aqua complex. That's why it's having a wine red color. So we will take this one. You can add probably around 1 to 2 ml of this aqueous cobalt chloride solution into the test tube. So I'll take probably around 2 ml to see the observation. Okay, now this is a cobalt chloride solution. Now we are going to heat the solution under Bunsen burner and see what's happening. Okay, so now we heated the solution under Bunsen burner. So as you can see that now the solution turns to deep blue color. So you can see that when I shake along the sides, see the color of this one. So it was wine red before, and after heating, the solution turns to deep blue in color. Okay, so now what kind of information we can gather from this experiment? So you go back to the equilibrium reaction. So this is the equilibrium reaction. So as you can see here, the cobalt, aqueous solution of cobalt will react with Cl minus ion. So the Cl minus chloride ions is already there in the solution. Why? Because we took cobalt chloride. The cobalt chloride is dissolved in water. It is already having Cl minus ion. Okay. Now when you take this one in the test tube and when you heat it, you can see that the color turns to deep blue. So you look at the equilibrium reaction. Cobalt hexa aqua complex, which is having wine red color, but your cobalt tetrachloride is having deep blue color. So from your observation from the test tube, it's very obvious that when you heat, the equilibrium is equilibrium is shifting towards the right side. So you're getting more and more cobalt tetrachlorocomplex. Okay, now as we see or as we studied, in an equilibrium we have two off reactions, right? One is the forward reaction, other one is the backward reaction. Now from this observation, you have to find out the endothermic reaction or exothermic reaction. Which one is endothermic or which one is exothermic reaction? If the forward is exothermic or if the backward reaction is exothermic. So you can write this information in your experiment data sheet when you submit the report.